Hello everyone, welcome back. So in today's video, we are going to solve some problems from 2024 exam. So we'll start from the last problem of paper 1. Okay guys, so before we begin, I just want to say that I'm making this video so that even 25 and 26 aspirants can also learn something. So I'm not making really quick solutions, okay? So I'll be discussing each option with enough detail. Okay, so let's begin with this question. So the question states that we have a circuit that contains an inductor L, a capacitor C0, and a resistor R0, and an ideal battery. So the circuit also contains two keys K1 and K2. Initially, both the keys are open and there is no charge on the capacitor. At the instant, the key K1 is closed, and immediately after this, the current in R0 is found to be I1. So basically, this is the key that was closed initially. So this is our active circuit. Now they're saying immediately after this is closed, what is the current in the circuit? Okay, so this is our active circuit over here, and we have an inductor present over here. Okay guys, so if you have a branch in which an inductor is placed, then the current through that particular branch cannot immediately change. And by immediately, I mean, so let's say if I close the circuit at time t equal to 0 seconds, then the time at t equal to 0 plus, which is 0.0000, you get the idea, right? 1 second. Even at that time, the current is the same. You can explain it in multiple ways. So one way is that the energy of the inductor is half Li squared, right? And in order to store the energy in the inductor, it does take some finite amount of time. And by finite, I mean like 1 millisecond or something like that, right? So it cannot be instantaneously changed in a very short time frame. So keeping this fact in mind, we can say that once the key is closed, just before closing the key, the current in the inductor branch was 0, which means right after closing also, the current will be 0. And therefore, we can say that I1 is actually 0. Or another way, you can also treat it like an open circuit. So let's further continue reading the problem. So after a long time, the current attains a steady state value of I2. Okay guys, so after a very long time, what they mean by saying this is that the current achieves its steady state value, which means di by dt is 0 after a very long time. So what that means is, and so the potential drop across the inductor is L di by dt, right? So if di by dt is 0, it means that the potential drop across the inductor is 0, which means we can treat it like a short circuit. So after treating this like a short circuit, the current I2 you can simply find using Ohm's law. It will be 20 by 5, which is 4 amperes. Okay, so I2 matches with 3. Okay, so the value of I2 is 4 amperes. Okay, so now the thing is key K2 is also closed and simultaneously K1 is opened, and the voltage across C0 oscillates with amplitude of V0 and angular frequency of omega naught. So we have to find both of those values. So K2 is closed and K1 is opened, and these both are done simultaneously. Okay guys, so again, as I said earlier, the current through the inductor branch cannot change instantaneously. So just before, we do the switching operation, the current in the inductor was I2, right? So just after switching K2 on, also the current in the inductor branch will be I2, which is 4 amperes. So now here we have an inductor and a capacitor circuit, right? And now the bottom circuit is useless. A lot of you guys may already know the formula for omega naught. It is 1 by square root of LC. I will just be solving the differential equation, okay? Okay guys, so basically the fastest way to do this will be, you already should know the formula that omega naught is 1 by root LC, and then you can simply do energy conservation, right? So if we know the initial maximum current in the circuit, I naught, so the initial energy is half Li squared, so and the final energy, and obviously now the energy will be oscillating between the capacitor and the inductor, right? And when the voltage across the capacitor is maximum, all of the half Li square energy will be converted into the energy stored in the electric field of the capacitor. So you could say half CV naught squared equals half Li squared. Okay, so this is certainly the easiest way to solve it, but I'll just show you how to solve the differential equation. Okay guys, so now let's say at time t equal to 0 we close the switch, so we can say at time t equal to 0 the current in the circuit is 4 amperes, right? Let's say after some time t has passed, the current in the circuit is I. So now we can write the KVL equation for this loop over here. So let's say this is the positive plate of the capacitor and this is the negative plate, and the charge on the positive plate is Q. So now the potential drop across the inductor is minus L di by dt. So basically what you do is assume a direction of current, and in the direction of current write the potential drop as minus L di by dt. And now as we go from the positive plate to the negative plate, the drop is going to be minus Q divided by C, and this would be equal to 0. So this is the KVL equation. So let's get rid of the minus sign and write it as plus. So now the second equation is, we can say that dQ by dt which is the rate of change of charge on the positive plate of the capacitor, will be equal to the current in the branch, right? Which is actually nothing but I itself. So I can say dq by dt is nothing but I. So here di by dt, I can write it as the double derivative of q. So I can say L d square q upon dt square plus q divided by c equals 0. So from here the double derivative of q actually becomes minus q divided by LC. So now this differential equation, guys, is exactly the same differential equation that we get in the case of SHM, or simple harmonic motion, right? And the solution over there was a sinusoidal one, right? So here also it will be a sinusoidal function, and we call this coefficient of q as omega squared. So omega squared is nothing but 1 by LC, which is the angular frequency of oscillations. So we can write down the solution q as a cos omega t plus b sin omega t. Okay, so now you may say, why didn't I write a sin omega t plus phi? First of all, it's the same, okay, because even here there are two unknowns, and in a sin omega t plus phi also there are two unknowns. But there is one advantage of writing it this way, and that will be clear in a bit. So the first condition is that at time t equal to 0, the charge is 0. Right, so if you put t equal to 0 here, you can see that the sign term just dies off, and what we are left with is a. So we can directly say that a equals 0. Okay, so now the charge q is b sin omega t. So now how do I determine b? For determining b, what we can do is relate it to the current. So we know at time t equal to 0, the current in the circuit is 4 amperes, right? So the derivative of this dq by dt is b omega cos omega t. So if I put t equal to 0 here, it will be b omega. So the value of b is nothing but 4 divided by omega. So finally our charge as a function of time turns out to be 4 by omega cos of omega t. And here omega is again 1 by root LC, which we can actually calculate. L is given to be 25 mH and capacitance is given to be 10 microfarad. So this, after solving, turns out to be 2000 radians per second. Now guys, they asked us the value of omega in kilo radians. So that would be 2000 divided by 1000, which is 2. R will match with 2. Okay. And now what is the value of V naught? So the voltage V across a capacitor, we can write it as Q divided by C. Right, so the maximum voltage V naught will be the maximum charge, which is 4 by omega divided by the capacitance C, and this will, after solving, give you the answer as 200 volts. So option S matches with fifth option. So the answer to this question will be A. Now guys, this is not the best method to solve this. A better method is to just remember that for an LC circuit, the value of omega is 1 by root LC, and then use energy conservation. Okay, so maybe we can discuss that point a bit. Wait a second, so this would be sin omega t. Okay guys, so if you observe something, the charge function of the charge and the function of the current are 90 degree out of phase. It basically means that when the charge is maximum, then the current is 0, right? I mean, that we can also decide using energy conservation, right? So using energy, we can say half Li squared plus half Cv squared, which is the total energy of the LC circuit, is some constant K. So as the current decreases, the voltage across the capacitor will increase, and these will keep on oscillating. So this will directly give you the answer as 200 as well. But I wanted to discuss the differential route. So yeah. So now let's move to the next question. Alright, so this is problem number 16. It's from geometrical optics. So we have a light ray that is incident on the surface of a sphere whose refractive index is n, and its angle of incidence is given to be theta naught. Okay, so let's draw the situation first. Okay, so we have a sphere, and let's say this is the incidence point. Okay, and let's take the incident ray to be along the horizontal. So the incidence angle is given to be theta naught. Refractive index of the sphere is given to be n. Okay, so now it's given the ray partially refracts into the sphere with an angle of phi naught and then partially reflects from the back surface. The reflected ray then emerges out of the sphere after a partial refraction. So we have to figure out the total angle of deviation of the emergent ray with respect to the incident ray. They're calling it alpha. So they're saying the ray refracts once and the angle of refraction is going to be given to be phi 0. This triangle is an isosceles triangle, guys. So even this angle is going to be phi naught. Now it's given that it undergoes partial reflection at the back surface. So even this angle is going to be phi 0. So now let's connect it to the normal. Okay, and then it undergoes refraction at this particular surface. So even this angle is phi 0. Okay guys, so if the light ray is incident at an angle of phi 0, then it refracts at an angle of theta 0. Okay, if you apply Snell's law at this particular point, at this point of incidence, then we can say sine theta naught, n sine phi naught. This is a question that we have to solve option by option. In option P, they are saying if n equals 2 and alpha is 180. Okay, which means that the incident ray and the final emergent ray are anti-parallel. Then all the possible values of theta naught is. Okay, so first let's try to determine alpha, the general value of alpha. So alpha is nothing but the net deviation in the light ray. Now as these individual light rays are just straight lines, we can add their individual deviations and then sum it all up, right? So the initial light ray, it bends in the clockwise sense by this particular angle, and that we can easily determine. This full angle is actually theta naught and this small angle is phi naught, which means it bends by theta naught minus phi naught. So this angle through which the first light ray deviates by is theta naught minus phi naught in the clockwise sense. Okay, now let's look at the second incidence. So here the light ray bent by this much angle. This angle is 2 phi naught and this angle will be pi minus 2 phi naught. So the second light ray, it bent by an angle of pi minus 2 phi naught in the clockwise direction. So now let's look at the third light ray. So this also bent by an angle of theta naught minus phi naught in the clockwise sense, right? Even this bent by an angle of theta naught minus phi naught. So if you observe, all the light rays are bending in the same sense, right? So we can just add their net deviation. So the deviation at the first point is theta naught minus phi naught in the clockwise sense, and at the second point it is pi minus 2 phi naught again in the clockwise sense, and the third point is again theta naught minus phi naught. So I can just double this, okay, and say that this is equal to alpha. So now in the first option they have given the value of n equals 2, okay, and alpha equals 180 degree. So if I substitute alpha equals pi, then pi cancels out, theta naught equals 2 phi naught. So this is the first relation, and we also know that n equals 2, so we can substitute that in the Snell's law equation. Now guys, we need the value of theta naught, so we can say sine of theta naught equals the refractive index n times sine of phi naught, and phi naught I am going to substitute as theta naught divided by 2. From here we can say cos theta naught by 2 is actually 1. So of course the value of theta naught equals 0 is true. So between 0 and 180, the only useful answer is theta naught equals 0. So P option matches with 5. Okay. So in option Q, again alpha is 180 degree, which means this relation is still satisfied, but they're saying the value of n is root 3. So the Snell's law expression will change. So for Q option, we can say sine theta naught. So cos of theta naught by 2 becomes root 3 by 2. So theta naught by 2 is actually equal to 30 degrees in this case, right? So from here, the value of theta naught is 60 degrees. Okay, so this is the only possible value. So the only possible values of theta naught in this case is 60 degrees. If you check the options, they're saying 60 degrees and 0. Now in the options, they mentioned alpha equals 180 degree, right? Alpha equals 180 degree is always true for theta equal to 0 degree. If the incidence angle is 0 degree, then the light ray will go hit the other surface because this is passing through the normal, right? And it will get reflected. So if theta or the incidence angle is 0, then alpha will definitely be 180 degree. And this is true independent of the refractive index. Okay. So 0 degree will always be the answer, no matter what. So Q matches with option 2. In our option, also they're given the value of alpha is 180 degree. Then they're asking the possible values of phi naught. So we already know that phi naught equal to 0 will be a solution. Okay. So now phi naught is nothing but theta naught by 2, right? So basically cos of phi naught is again root 3 by 2. So again phi naught can only be 30 degrees in this case. So the answer to option R will be 30 degrees and 0. So which is first option. Now in option S, they're saying, so if n is root 2 and theta 0 is 45. So sine 45 equals root 2 times sine of phi naught. So from here phi naught turns out to be 30 degrees. And they're asking the value of alpha. The value of theta naught is 45 degrees. Phi naught we calculated it is 30 degrees. So we'll substitute it into our alpha expression in the clockwise sense. So the ray bends by 150 degree in this case. So the possible value of alpha is fourth option. Okay, so S will match with 4. So yeah, so the answer to this question is option A. So now let's move to problem 15. Okay, so in this question we have 4 identical thin square metal sheets, S1, S2, S3 and S4, and each of them are squares with side A, and they're kept parallel to each other with equal distance of d. So basically the capacitor formed by any two of the adjacent plates is epsilon naught a square by d, right? Epsilon naught a by d, and this is what they have given as C naught over here. So again guys, so in this question everything is almost similar, so I'll just choose the easiest options. So if you observe, if I solve option S, then I can directly eliminate 2 options. So I'll start with option S. Okay, so let's draw 4 plates. Okay, and in the last option they're saying the capacitance between S1 and S2, so that will be this plate and this plate. So we have to find the capacitance between these 2 plates. S3 is shorted to S1, this plate is connected to this plate, and S2 is shorted to S4. So I'll just connect it using this wire. So S2 will be connecting to S4. Okay, so this is the circuit that is given to us. Okay, so first you need to understand guys this, so these 4 plates, you know, if you take one pair at a time, they will form 3 capacitors who each of whose capacitance is C naught. Okay, so now what I'm doing is I'm trying to draw the equivalent circuit for these 4 plates. So I know that there will be 3 capacitors, so I drew 3 capacitors. Okay, and I split this middle plate into two plates, something like this, and then I connected them with a connecting wire. And I did the same for this plate as well. I split it into two plates and then I connected it with a connecting wire. Okay, now plate 1 has a connection with plate 3, right? So now plate 1 is over here, right? So I'm going to use a different color. So this is the connection from plate 1 to plate 3, and now plate 2 is connected to plate 4. So plate 2 is over here and plate 4 is at the end. So okay, so the connection is going to look something like this. And then we have to figure out the capacitance between this point and this point, right? So this is going to be the equivalent circuit. So let's say this node has a potential of 0. So even this would be 0 and even this would be 0. And let's say this node has a potential of x. So this would be x, this would be x, and this would be x as well. Now even this is going to be 0, right? So if you observe something, guys, this capacitor is across the potential of x and 0. This capacitor is also across the potential of x and 0. And similarly, this guy is also across x and 0. So basically these three capacitor plates are in parallel. So if these three capacitor plates are in parallel, then we can say its equivalent capacitance would be the sum of their individual capacitance. So the answer is nothing but 3C0. Okay, so option S should match with option 1. So I can disregard option A and D. So now let's solve option R. So it's given that we have to find the capacitance between S1 and S3 now. So S1 would be over here and S3 would be over here, right? And S2 is shorted to S4. So the second plate is connected to the fourth plate. So now this is the equivalent circuit. So let's mark potentials. So let's say this is 0. So even this point is going to have a 0 potential. Let's say this node is X. And let's say this node is Y. So here if you observe this capacitor and this capacitor will be in parallel. So you can flip this capacitor and put it in on top of this guy and observe. These two capacitors will be in parallel. So their equivalent capacitance is going to be 2C0. So I can just erase this guy and write its equivalent capacitance as 2C0. And now 2C0 and C0 are in series. So their equivalent capacitance is going to be 2C0 by 3, right? Simply C1 C2 by C1 plus C2. So option R should match with 4. So R is 4, S is 1, option C will be the correct answer. So now let's do 14th question. Okay guys, so this is problem 14. We have been given 1 mole of a monoatomic ideal gas that undergoes the cyclic process as shown in the figure JKLMJ as shown in the PT diagram. So they have given us a pressure versus temperature plot. So basically process JK and LM are isobaric processes, right? Constant pressure processes, and process K to L and M to J are isothermal processes. So if you read option S first, they're saying the change in internal energy of the gas in process MJ. Now MJ is an isothermal process. So isothermal meaning temperature is constant, right? Now internal energy is a function of the temperature. So if the temperature is constant, then that means the internal energy remains unchanged. So the change in internal energy of the gas in the process MJ should be 0. So S would match with option 2. Okay, so now the next easiest option to solve is the change in internal energy of the gas in the process JK. Now guys, the change in internal energy for an ideal gas, we can directly write it as NCV delta T. So if I know delta T, then I can easily determine it. So the number of moles is 1. Gas is given to be monoatomic, so CV will be 3R by 2. And from J to K, as you can see, the temperature is increasing. So delta T is positive and it is equal to 3 minus 1, which is 2 T0. So here the answer turns out to be 3R T0 and positive. So Q should match with option 3. So as you can see, the only option that matches is option B. So I'll just solve the other options as well. So now we have to talk about the heat given to the gas in process KL. So K to L is an isothermal process, guys. So let's apply first law of thermodynamics for the process K to L. So we can say Q equal to delta U plus work. So again guys, as it is an isothermal process, delta U is 0. So the heat transfer is just going to be the work done by the gas. So and if you observe, temperature is remaining constant and pressure is increasing, right? So now the process is isothermal. So what that means is temperature is constant, or we can say P times V is a constant. So if the pressure is rising, then the volume must go down. So this process is actually an isothermal compression process. So as it is a compression process, the work done by gas will turn out to be negative, right? So the heat is actually released in this case. So now the work done, you can simply find it out using integral of PdV, and the direct result is nRT ln of V2 by V1, and most of you may be familiar with this. Otherwise what you can do is you know the fact that PV is nRT, so you can substitute for the value of P as nRT by V into this expression and integrate it. So the work done will turn out to be, number of moles is 1, the temperature here is 3 T0 times ln of final volume upon initial volume. Now guys, if you observe, the pressure actually doubled in going from K to L, which means the volume will actually become halved, right? So the final volume is going to be 0.5 times the initial volume. Ln of 0.5 I can write it as minus ln 2. So this just becomes minus 3r t naught ln 2. So option R will match with option 5. So now there is only one option left, that is option P. So we have to figure out the total work done. Now let's do it real quick. So K to L, it is minus 3R T naught, Ln 2 as we determined. Now M to J, again it is an isothermal process, guys. So here it will be N T naught ln V2 by V1. So here if you observe, the pressure is becoming 1/2, which means the volume will double. So this is going to be ln 2. So here the work done will be R T naught ln 2. Now J to K and M to L, these are both isobaric processes. So now for isobaric processes, we can say the work done is integral PdV again, but the P itself is constant, so we can say it is P delta V. So if pressure is constant, then the volume is directly proportional to the temperature. So here the temperature is becoming 3 times. So if I take the delta on both sides, P is constant, so P delta V, I can write it as nR delta T. So instead of this, I can also use the formula nR delta T. So J to K, nR delta T is going to be R 2R T naught, and it is going to be plus because delta T is positive. And from L to M, it is going to be minus 2R T naught. So if you add all of them, the total work done just comes out to be minus 2R T naught ln 2, which is option 4. So P matches with option 4. So the answer to this question is option B. Okay, so now let's do problem 13. So this is problem 13, guys. So problem for mechanics. So in this question, we have a thin uniform rod of length L and a certain mass, and it is kept on a frictionless horizontal table with a massless string of length L fixed to one end. So this string is fixed to this end, and this is the rod that they are talking about. If a horizontal impulse P is imparted to the rod at a distance of x from the midpoint of the rod, so this is the midpoint of the rod, and the line of action of the impulse is at a distance of x, then the rod and the string revolve together around the point O, with the rod remaining aligned with the string. Okay guys, so this is a situation given to us. So both the rod and the string have the same length of L, and an impulse of P is applied at a distance of x. Okay, and the next thing that was given to us is that the rod will move along the path of the circle along with the string, right? So after some finite amount of time has passed, the situation would look something like this. Okay, first thing that we need to understand is, in order for this situation to be possible, the omega of this entire line has to be the same. So let's hypothetically say the angular velocity of the circular motion is, let's say, omega. So this point must move with a velocity of L omega, and this point must move with a velocity of 2L omega. Okay, so this distance is L and this distance is 2L. Only then the rod will be able to move along this circular path. So let's see what will happen if that's not the case. Okay, so now let's say if this point had a velocity of L omega, and this point, instead of having 2L omega, had a velocity of, let's say, 4L omega, then what would happen is, let's say after rotating by a very small angle theta, the rod would actually rotate way more. So basically the rod would look something like this. Okay, they won't move along the same circular path. Okay, in short, we can say that the omega with which the rod is rotating about its center of mass, okay, let's call it omega cm, this has to be the same as the omega of the circular motion. Okay, otherwise if omega of the rod is greater, then the situation that I depicted will happen. This rod will rotate more than the string, which is not what is being asked in the question. So both of the omegas must be the same. We can also see it in another way. So let's say the string rotated by an angle of 60 degrees. So if you observe something, the rod also rotated by the same angle, 60 degrees, right? So basically the angle rotated by the string is the same as the angle rotated by the rod about its own axis. Okay, so and if when it's rotated by 90 degree, then the rod will be vertical. So as you can see, the rod also has rotated by the same angle of 90 degree. So in short, the omega of the rod must be the same as the omega of the circular motion, or basically the revolution omega. So now the velocity of the center of mass right after the impulse is applied, let's say it is V. So obviously guys, the only force acting on the rod is the impulsive force, right? The string first of all cannot apply any shearing force, and on top of that, a tension is 0 anyway. So the only force is P, so we can apply impulse momentum theorem, so and we'll get the velocity V as P divided by M. Okay, and secondly, the omega of the rod about its own axis, let's say it is omega naught. Omega naught we can determine using angular impulse. So about the center of mass, the angular impulse is going to be the impulse P times the distance x, and P into x would be I omega naught. So I'll divide it by the moment of inertia of the rod about the center of mass, which is ml square by 12. So now we figured out the omega of the rod. Now what is the omega of the circular motion? So that is pretty simple. The velocity of the center of mass is v, and the distance of the center from our point O is 3L by 2, right? So the omega of the circular motion is V divided by 3L by 2, and omega of the rod is Px upon ml squared, and P I'm gonna substitute as m times V, right? So this will be m Vx divided by ml square by 12, and from here x turns out to be L divided by 18. Okay, and they wanted the value of this n, so that would be 18. All right, so now let's move on to the next question. Okay guys, so in this question we have two large identical water tanks, 1 and 2, and they're kept on top of a building of height h, and they're filled with water up to height h in each tank. Both the tanks contain an identical hole of small radius on the sides close to their bottom. Okay, pipe of the same internal radius as that of the hole is connected to tank 2. So and the pipe ends at the ground level. When the water flows from tanks 1 and 2 through the holes, the time taken to empty the tanks are T1 and T2 respectively. And then they've given a relation between capital H and small h. So we have to find out the time to empty the tanks in both of the cases. Okay, so this is the condition given to us. There is a tower of height h, and on top of that there is a water tank in which water is filled up to height h, and then we have a small hole that is at the bottom of this container. Okay, and let's first talk about the case for tank 1. Okay, so in the case of tank 1, only the hole is present and water flows out of the hole. We need to find the time of emptying. So the first thing is that if you apply Bernoulli's theorem about from the free surface to the hole, you'll figure out that the velocity of efflux, which is basically the velocity with which the fluid is escaping the hole, turns out to be square root of 2gh, right? Where h is the distance of the free surface from the hole. So if I want to figure out the volume flow rate of the fluid escaping through the hole, it is simply the area of cross section of the hole multiplied by the velocity v, right, which is square root of 2gh. Okay, so this is also the rate at which the volume of the tank is decreasing. So the volume of the tank, guys, I can also write it as the area multiplied by the height. So the rate at which the height of the tank is decreasing is minus small a upon capital A times square root of 2gh. So this is the differential equation that governs how the height is reducing with respect to time. So let's consider the 1D equation of motion. V square equals u square plus 2ah. Okay, so if I assume the initial velocity to be 0, then this is v square equals 2as, right? The velocity v is nothing but the rate of change of the displacement, right? So guys, if you observe something, this is exactly similar to this. The only difference is that there's a slight difference in the acceleration, right? Here the acceleration is g, here the acceleration is going to be g multiplied by the square of this term, right? So the simple point is that dh by dt, which is the rate at which the height of the surface is going down, the acceleration of the surface is going to be a constant. So this is a formula from 1D kinematics. We can say that the average velocity, which is u plus v divided by 2, okay, you can also say this is the average speed multiplied by the total time t, is actually equal to the total displacement. Okay, and you can easily prove this using s is equal to ut plus half at square and v equal to u plus at. Just eliminate acceleration and you'll get this expression. Now the advantage of this expression is that I don't even have to do any integration. I don't have to do anything. All I need to know is the initial velocity, initial value of dh by dt, final value of dh by dt, and the displacement. So in the first case, for the tank number 1, what is the initial value of dh by dt? In terms of magnitude, it is small a by capital A times root 2gh. So small a by capital A times square root of 2gh. In the final case, guys, the entire tank is empty. Now, obviously, once the tank is completely empty, dh by dt would be 0, right? Because there is no fluid going out. So the final velocity is 0 divided by 2 times the time taken to empty the tank T1. Let's say it is T1 equal to h. Displacement is nothing but distance traveled by the free surface, which is going to be h, right? So the right side would simply become small h. So this is going to be our equation number 1. Now the second case is a bit more interesting. So now in the case of the second tank, guys, they attached a pipe over here through which water will flow out at the bottom. Okay, so here let's say, guys, the velocity with which the fluid is exiting the pipe is small v. So now we can consider a streamline between the free surface and the bottommost point, and we can apply Bernoulli's theorem here. Here also, you guys can do this as an exercise. So here the pressure is P0 and the velocity of the free surface is almost negligible. So you can apply Bernoulli's theorem and you would observe that here also the velocity will just turn out to be square root of 2g small h plus capital H. The expression looks exactly similar. It's just that the hole is now at a depth of small h plus capital H, right? So in short, what I'm trying to say is, if I replace this situation with an alternate situation in which the tank looks something like this, and the water is filled up to a height of small h plus capital H. And here, if I pierce a hole at the bottom, the efflux velocity is going to be exactly the same as this particular value. So basically, I can consider this case to be equivalent to this case, is what I'm trying to say. So now we can directly apply our time of emptying result, right? Here, the initial efflux velocity is going to be small a divided by capital A times square root of capital H plus small h, right? And finally, guys, we want to completely empty the small tank, right? So imagine this is filled up to a height of h, and now it is emptied, and now it is being emptied, and when it is fully emptied, we need to report this particular time. So here also we'll empty it up to a height of h, right? So the final height of the container is capital H. So the final efflux velocity here in this case is going to be square root of 2g capital H. Okay, so this will be plus small a by capital A square root of 2g capital H. So this is u plus v divided by 2. So I'll take it to the next page now. This is u plus v divided by 2 times the time taken in the second case equals to the displacement. And guys, if you observe, the free surface of the fluid displaced by the same distance of h in this case as well, right? So here the RHS is still going to be h. So this is equation number 2. So now we'll just equate equation 1 and equation 2. And then if you take the ratio of T1 and T2, it will turn out to be 9 by 3, which is 3. The answer to this problem is going to be 3. It will take 3 times the time to empty tank 1 in comparison to time taken for tank 2. Okay, so now let's also solve question 11. Okay guys, so this is problem number 11. So it's a straightforward problem from Doppler's effect. So we have a source of sound S that has a frequency of 240 Hertz. So F0 is given to be 240 Hertz. The observer O and the source S is moving towards each other with a speed V with respect to ground. So in this case, guys, the apparent frequency, let's call it F1. So that would be F0 times the speed of sound plus the speed of observer, which is actually V in this case, divided by the speed of sound, speed of the source, which is V. So, and this is actually given to be 288. And in the second case, they are given to separate, move away. So in this case, the apparent frequency is going to be F0, Vs minus V divided by Vs plus V. And this is actually given to be n hertz. So now we can just multiply these two equations. So these two terms cancel out. So we get F0 squared, which is 240. 240 times 240 divided by 288 turns out to be n. 288 is 144 times 2. So 144 is 12 into 12. So this becomes 20. This is also 20. So the answer is going to be 200. So n is actually 200 hertz. So guys, I'm ending this video here. So the other problems we'll solve it in another video. And yeah, if you enjoyed the video, please do like, share and subscribe. And that's it. Thanks for watching.